We will see. I mean, I figured since someone put beyond in the title of my talk, I should put a beyond. Wasn't me. I looked at the program on the website, and there was beyond. So I figured I should do beyond. I have a slide for beyond.
Okay. So welcome everyone to the afternoon session. We're very happy to have Severin. He's going to talk to us about the city of Baku and beyond and answer all the questions that appear just before the lunch.
Indeed, yeah. Luckily, this is a topic we haven't mentioned yet so far. And when preparing these slides, I realized this is actually a fairly tedious task. But luckily, this year was a very nice review on that topic. I think it appeared. Should I speak up? I think it's not working for the room, right? Which I think appeared on April 3rd this year. And I figured I would just follow this review page by page. So that made my task easy. Are there any questions? I hope the speaker after me prepared enough material. Questions? Okay. Fortunately, there's more material, so I can talk about something. And these are a few recent review papers that turned out to be quite helpful. Also a few older ones, which I find very helpful. And in particular, I followed. I had quite a lot of looked quite closely at this first one, which was really helpful in preparing these slides. So if you know it, some things you will recognize. And I should make the usual disclaimer. Since this is a review talk, I'm to the largest extent I'm not talking about my own work, and I'm afraid it will be inevitable that I will miss some important pieces of work, that I will miss some references. In case so, please let me know, and please don't feel offended. Anyway, I would like to start with a brief introduction why this is an interesting and probably also difficult topic. Since, I mean, many of you are experts, some of you will find this maybe a bit boring, but I hope at least for some of the younger people it will be instructive. So, of course, if we, and this I think also ties nicely to the previous discussion we had, if we look for realistic string theory vacua, they should satisfy some properties, like they should probably be four-dimensional, they should have broken or no supersymmetry, they should have dark energy, for example, in the form of a positive cosmological constant, and certainly many other properties, like, for example, the standard model. Obviously, here I'm going to focus on these two things, no supersymmetry and dark energy or positive cosmological constant, so to say, de Sitter vacuum. On the other hand, in string theory, the vacua that we understand very well are kind of in the opposite corner. They typically have extended supersymmetry in four dimension. That means n larger than 2 or equal to 2. And typically they have a negative or vanishing cosmological constant, so they're ADS or Minkowski. And of course, these two properties are not independent, because we know if we have a positive vacuum energy, we necessarily need to break supersymmetry, because we don't have a supersymmetry algebra with, I think, unitary representations in de Sitter space. So, and I think this is also, from a technical point of view, one of the most challenging questions when actually trying to answer this question, whether string theory has de Sitter vacuum or not. And I would start with the bold claim that so far we are not completely sure yet whether string theory has stable, or I should probably put metastable, neither non-supersymmetric vacua nor de Sitter vacua. Of course, you will say, okay, we actually studied non-supersymmetric string theory a lot, and we know a lot about non-supersymmetric string theory. Here are just a few examples. However, I really want to emphasize this point that I'm trying to talk about vacua here, and in particular metastability. So I want to be at the bottom of the potential, which also is a question that connects to Thomas' talk from yesterday. There's a question, I believe. Yes. Okay, that is a very good point. Thank you. I think we have a discussion session later on de Sitter vacua, so maybe I can just refer that to the discussion session, even though it's an ADS point and not a de Sitter one. But thanks a lot. I believe Miguel had also, but maybe he also wants to. Right. Anyway, so my point is that so these classic examples of non-supersymmetric string theory, we always have some form of tachyonic instability or runaway potential, and that actually points to one of the biggest difficulties in constructing de Sitter vacuum string theory, which is actually observation, which is very old, namely the Dine-Seiberg problem, which tells us that when we study string theory compactification, we have moduli, like geometric moduli or just the string coupling, which appear as massless scalar fields in our tree-level classical string theory. And whenever we break supersymmetry, we are in general not protected from quantum effects. So these quantum effects generate a potential for the moduli. However, when we go to some limit where we send these moduli, for example, the string coupling or the inverse string coupling to infinity, we restore somehow a weakly coupled regime. Typically, we restore supersymmetry where effective tree-level description is valid. And in this limit, we expect our potential to vanish. This is also a point which was analyzed quite a lot recently in the context of the Swampland program. But following this intuition, if we add quantum corrections to that story, basically two things can happen. We get a potential either like that or like that. And if, which clearly doesn't have a minimum, but some form of runaway. And if you want to obtain some form of minimum, we should add higher order corrections to get a minimum like this or like that. But you would expect to get a minimum from higher order corrections. These corrections somehow have to compete with your first order corrections. So they should be of at least similar order than your first order corrections, which then leads you to conclude that all your corrections are somehow of a similar order, which makes you question whether you can take a perturbative approach at all. So you would probably conclude that if you have a de Sitter vacuum here like that, you are somehow in some strongly coupled regime. And in the perturbative regime where you can somehow know what you're doing and where you trust what you're doing, you would expect a runaway potential like that. Evidently, this is not, oh, I had another slide here, where I basically just wanted to highlight this nice quote from Frédéric Deneff's lecture notes. Very good. Anyway, what I wanted to say, I mean, we know that this is not the end of the story. There's another ingredient, or there's another thing we can try, namely to stabilize moduli already at the classical or tree level. And the ingredient we all know and like a lot are fluxes. And it is well known that fluxes generate a potential for the moduli. For example, we see that easily by looking at their kinetic terms in a higher dimensional action, where the metric of our internal space appears. So this gives some dependence on the moduli. And however, if we proceed naively with just this term in the action, we get a potential for our moduli, for example, the radius of our internal dimension. However, we typically get a decompactification. We get a runaway potential to decompactification. Still, this is not the end of the story. And I think also Thomas in his talk gave a very similar argument. We can try to balance, for example, this against the curvature of our internal dimension, which also has a radius-dependent potential. So we get a overall potential, which we could write as a sum of these terms. However, if you sum up these terms, you can easily check that this potential satisfies the inequality of this form. So on its own, you will not find de Sitter vacuum just from fluxes and curvature. On the other hand, I mean, it's we all know that ADS minima of this form are very easily obtained. And this was formalized by Balmaceda and Núñez and many follow-up works in some no-go theorem that basically from any two-derivative supergravity, we will not find a smooth compactification to de Sitter. So we necessarily have to add some form of string theory ingredients, for example, in the form of quantum effects or stringy ingredients like higher derivative terms and typically also orientifold planes. So our compactification will not be smooth, but will have some form of string theoretic singularities. And this, of course, then again opens the box of the potential danger of Dine-Seiberg-like issues. So we have to make sure that we get these string theory or corrections under control. Yes. I'm not sure I know what you mean, but I mean you have to make some assumption on like what kind of energy condition, for example, your sources satisfy, which is, for example, not satisfied by O planes. Why, for example, O planes? Right, but I think you can rephrase that again in terms of some energy condition. I mean, you could have, for example, like in type 2a, some Romans master. Okay. Thank you. Anyway, so if I don't know, if I give a sketch of my string theory moduli space, it's fair to assume that if I really go to some asymptotic limit, it will be very hard, if not impossible, to find a de Sitter vacuum. On the other hand, once I go to somehow slightly, at least to the interior of the moduli space, I can use these ingredients, and I have a chance of finding de Sitter vacuum. And then essentially the question is like how far the boundary, or how far into the interior where we don't really know what's going on do we have to go. So with these insights, somehow the most promising strategy is probably to combine different effects, classical and corrections, to avoid the blind sample problem. Okay, let me now try to give some overview over various string theory de Sitter constructions. And I'm trying to follow a bit this classification here, which I shamelessly stole from this review paper, which tries to classify string theory de Sitter constructions along these lines. There's probably also other classification schemes possible. You could probably also try to classify them by the point where you break supersymmetry, for example. But let's somehow try to go at least roughly through the list and see what we can say. So the first thing is to consider effective action is to consider non-critical string theory. So string theory in a dimension different from 10 dimensions, for example, where in the effective action we get a term like that. And in particular, you observe that this term is positive if D is larger than the critical dimension. And having such a term actually facilitates finding de Sitter vacuum, even at the classical level, considerably. There were earlier models around the 2000s. However, what I would like to highlight here, there was a very nice paper by Daniel Junghans earlier that year, where he took a critical analysis of these kind of models. And in particular, he generalized certain Maldacena-Nunes like no-go theorems for these kind of setups. And what he found was that generally you have no parametric control in these setups over O-plane back corrections, and possibly also higher derivative corrections, which you possibly have to these actions in the limit where you send large D to the where you go to the large D limit. So if you try to use D as your control parameter, which is something you might naturally try in these models, you will not find parametric control, which I think is a very nice result. Let me shortly also mention non-geometric constructions, which is a topic I don't know much about. You could, for example, follow the nice review by Erik Plauschin. Generally, the idea is here to apply some chains of string dualities, in particular T-duality, to construct certain non-geometric background of fluxes. And the nice thing is that you if you try to compute the resulting four-dimensional effective potentials, they often allow for de Sitter vacuum. So this is a natural candidate to consider. However, almost by definition, these setups are in a way intrinsically string theoretical. So I think many people are not sure to which extent we can actually trust them. And there's a comment or question by Eric. Yes. I see.
It's the only one which comes to everything else. Is there Yankee identities that sits on that concept is not all stabilized. So I know only one model which comes close, that's the everything else is some problems that
Okay.
there's not tremendous evidence.
Okay, thank you very much for the comment. So Okay, let's try to continue our list. Maybe the most natural thing you can try to do is to find de Sitter vacua at the level of the classical geometry. So to solve your classical 10-dimensional supergravity equations of motion, assuming that your 10D spacetime contains a 4-dimensional de Sitter factor. And of course, from what we said before, such a setup must necessarily contain some O-plane or D-brane singularities. So you're not operating at the level of a smooth geometry. And of course, you must break supersymmetry already at the level of the classical geometry. So you, of course, reduce the amount of control, and you might argue that it is not clear whether you have an actual string theory background. There's a large existing body on literature on these constructions, which I can't cite all. And however, one should note that, to my knowledge, all existing solutions suffer from some form of problems, like they're either classically unstable or tachyonic, or at least we don't know whether they're classically stable. They might not be under perturbative control, for example. They have not a sufficiently large volume such that we can trust it in a supergravity approximation, or G string is not small enough. And they often also contain O-planes in a smeared approximation, which you might or might not like. All right. Let me mention again non-supersymmetric string theory. I think we will also have a couple of talks on that tomorrow. As I introduced in the beginning, if I just look at the perturbative worldsheet CFT, I of course have the problem that I always have a runaway potential for the Dillerton if I do like some first order string perturbation theory, which of course brings me again back to a Dine-Seiberg problem. Indeed, for the heterotic string theory, you can even show some powerful no-go theorems against de Sitter space from the worldsheet. However, it turns out that, as Mariana and collaborators showed in a recent paper, that even the stabilization, getting a true minimum for the remaining moduli, for example, in heterotic string theory, is challenging. And there was a nice paper a few years ago trying to analyze this from the target space perspective, slightly similar to the story on the non-critical string I mentioned earlier, where again a positive Dillerton potential might help you finding de Sitter vacua. And in this paper, they showed various no-go theorems similar to Maldacena in this setup. So let us maybe come to, from my point of view, the most promising setup, what I might call hybrid models, where I try to combine different effects, fluxes, and quantum corrections to avoid no-go theorems like Dine-Seiberg, for example. I could try to balance my first order quantum effect against the classical effect and try to avoid it in that way to maintain maximal control over my construction. And of course, the two main competitors here, which are both in the type 2B or F theory setup, are the KKT or large volume scenario, where the idea is to start from something which is well understood, like a Calabi-Yau compactification, which originally has n equals to 2, and somehow invent a scheme where I break supersymmetry gradually and try to maintain control, therefore, as much as possible. I also want to refer to the next talk by Bruno De Luca, where he, I think, will introduce another model which you can probably put at this point in the classification scheme. All right, let me briefly remind you about the KKLT model. I think I don't have to say too much. Also, Jakob gave a very nice overview yesterday. Often it's portrayed as a three-step model, where the first step is the compactification on a Calabi-Yau orientifold and the moduli stabilization with fluxes. The second step is moduli stabilization, is scalar moduli stabilization by non-perturbative quantum effects, or also using alpha prime corrections in the case of LVS. And then the third step is the breaking of supersymmetry and the uplift to a de Sitter vacuum by anti-D3 brane at the bottom of the warp throat. And the idea here, or why this model is appealing, even though it might look like a somewhat baroque construction, is that I, as I also said earlier, I start with something that I know very well, like a Calabi-Yau, where if I don't orientifold, I have an n=2 theory, which is very well studied and under good control. I break supersymmetry to n=1 with orientifolding and fluxes, but I try to do that in a way where I can maintain as much of my n=2 knowledge, and eventually I break supersymmetry either here or here in a way such that I can still maintain as much of my n=1 knowledge as possible. So let's try to go through the list of steps, even though I think one of the difficulties here is also that these steps should not always be taken as individual steps, but they, of course, talk to each other. But nonetheless, let's try to go briefly through the list of steps and maybe highlight a few developments of the recent years. So the first step is moduli stabilization with fluxes, or the huge landscape of flux vacua, which is often cited as a necessary criterion for these constructions, because I want a sufficiently high statistical probability to find myself in the right point in parameter space to realize these models. I would claim that until fairly recently, we had a few constructions, but not very many explicit constructions where we really gave explicit flux choices and computed the stabilization of complex structure moduli. However, there were these very nice statistical arguments. Now, I would claim we know much more. So we have, for example, by the Cornell group, and also some work by the Munich group, some very nice systematic construction of flux vacua with a very small W0. Jakob also already explained this in his talk yesterday. So we know that we can obtain flux vacua with a small W0. Another point that got some attention is the Tadpole conjecture I formulated with my friend from Saclay, which, if it turns out to be true, would constrain the size of the flux landscape considerably. There's also very interesting relations to asymptotic Hodge theory, as, for example, highlighted in the papers by Thomas Grimm. And we also saw some advances in automized or computer-aided constructions for finding flux vacua, which is particularly important if you want to find flux vacua in a high-dimensional complex structure modular space. We also saw some things about that in the talk by Jim earlier today. Let me go over to the second step, Kähler modularization by a non-perturbative effects. There was a few years ago some debate on how to realize gauge-Jino condensation from a 10-dimensional point of view. From my understanding, this debate is mostly settled. I think most of us consider this debate mostly settled by now. However, there's also another point made by Safseti, I think, which is not getting a lot of attention, whether studying such non-perturbative corrections on top of a classically running solution is satisfied. On the other hand, also again referring to the talk by Jakob, we saw some highly explicit constructions, particularly also for large H11, trying to realize these non-perturbative potentials explicitly and explicitly solving for F term minima of these potentials. On the other hand, referring here to the talk by Max Wiesner, I think so far we're still not having a very systematic understanding of genuine n equals to 1 compactification, and in particular the genuine n equals to 1 corrections in there. So there might be still some more work to be done here. And lastly, I would like to mention that if one takes a holographic picture of these KKLT vacua, there might be some things we are not understanding completely here in this regard. Yes, that's why I put a question mark.
The question was asked in the discussion session. Everybody
I would actually be very happy to. I would actually be very happy to hear some discussion about that point during. I think we have another discussion session on the zeta vacua. I would be very interested to hear other people's opinion. Well, I don't think we know all n equals to 1 corrections yet, do we? I think the question I want to raise is if we somehow did all necessary computations here or not. But again, maybe I can refer to the discussion session. Okay, let's go on. The third step is the anti-brane uplift. There was a while ago, there was a lot of discussion about backreaction effects of the anti-brane on the case throat. I think there was not so much activity on this question during the last few years. However, there was some nice papers by the Heidelberg group on curvature corrections to KPV that might change the story a bit, in particular change some bounds on the number of fluxes you need for control in some form. Very important point was also raised here, which is the so-called singular bulk problem, which argues that we might control over the O-plane back reaction unless we have a large number of Kähler moduli, basically because the region, by trying to fit the KS throat into the Calabi-Yau, the region where the back reaction of O-planes becomes difficult, might become too large. I would also like to highlight this paper here, which addresses this problem from a slightly different point of view. You might also want to ask if you have control over all mass scales, even though I think that at the end of the day, that's probably fine. And another question, proposal, which is in principle a very old one, but which was brought up again recently by Sven Krittendorf and Andreas Schachner, is what about uplift by fluxes, by non-supersymmetric fluxes? So what about forgetting about the anti-brane completely and just starting with non-supersymmetric fluxes in the first place? Yes. So the second point, so depending on how much flux you put on the A cycle, I mean that's controlling your the size and the curvature of your S3 at the tip of the throat. And if this is too small, in principle, you might get higher curvature corrections, which you should take into account when computing the KPV story. So the bound, I mean, there you get a bound on how much flux you need for the polarization of the polarized NS5 frames not to decay, and this bound might get altered if you take these higher curvature corrections into account. I think some of the authors, I think Simon is also in the audience and could comment. But I think that's basically the story. No, okay. Right. Yeah, this is this story here. All right. Very good. Of course, there's also the large volume scenario, which got a lot of attention, and I can't manage all details here. Of course, one important point to mention is that control here, that we need control over corrections, in particular because we already break supersymmetry at the Kähler moduli stabilization step. Again, I would claim that in particular in the non-supersymmetric setup, not all corrections are explicitly known. There was for example, very nice paper here a couple of years ago. There were some interesting estimates of the sizes of corrections in this series of papers, and the upshot there was that we move outside of the regime of control unless we have a tadpole charge of a certain size. So the upshot, if I understand correctly, is essentially the larger we make the tadpole charge, the better is the control generically over these corrections. And I would also like to highlight that there was also some analysis in a holographic context and also in the swampland context of these ADS vacuum. Some of these papers, I think, also commented on the KKT ADS vacuum. Okay, let me go a bit further. I call this de Sitter and quantum gravity. So, of course, question you could ask yourself, and I think many ask themselves, is whether the difficulty of realizing metastable de Sitter vacuum in string theory is there mainly a computational or control problem, or is there maybe even something conceptually wrong or difficult with de Sitter in string theory or supergravity. I mean, it could be also some combination thereof, that there's some conceptual reason why it is a computationally difficult problem, that we are always somehow pushed into regions in the moduli space where we might not have or might lose control. So if the answer turns out to be B, you of course want to ask, what is the fundamental reason why string theory and quantum gravity and de Sitter vacuum are incompatible? However, if the answer to the question is A, then of course we ask, how can we access de Sitter vacuum in the context of string theory and quantum gravity? One possibility is, of course, a top-down construction, as for example also highlighted in Jakob's talk. But we might also, of course, ask ourselves, maybe is there some indirect way to prove the existence de Sitter in string theory or quantum gravity. A lot of attention on this or related question comes, of course, from the Swampland program, most notably the de Sitter conjecture claiming that any potential in string theory, at least in the asymptotic limit, should satisfy a bound like that, which got a lot of attention. Similar is also the trans-Planckian censorship conjecture, stating that there should not be any sub-Planckian modes growing larger than the Hubble radius. Interestingly, implying the de Sitter conjecture in the asymptotic limits. Recently, we saw a lot of attention to the so-called species scale, the actual quantum gravity cutoff, which seems to satisfy a similar bound than the actual potential, even though the potential and the species scale are, of course, not exactly the same thing. Referring to Thomas' talk, another important question is, of course, the question of scale separation and whether one can formulate something like ADS or even de Sitter distance conjecture, and maybe not directly related to the question of existence or stability of de Sitter vacua, but more sometimes I think it's cited as being some form of weak gravity conjecture in de Sitter is the Festina-Lente conjecture. Of course, there's also other approaches. I want to be brief here because I don't know much about it from a more like quantum consistency point of view on de Sitter. There's, for example, the question whether a so-called finite quantum breaking time might put constraints on the consistency of de Sitter vacua in quantum gravity. There's the observation that there's no ice matrix formulation in de Sitter. I want to highlight this paper by Alec Bedroyer, who gives a holographic argument basically following this argument observation for the TCC conjecture. And finally, there's of course also the topic of de Sitter holography, which I think is not discussed a lot in this community, whether one can get some insight from a de Sitter CFT point of view, for example, on the existence of de Sitter vacua in a quantum gravity or string theory context. But of course, again, if you want to discuss this in a consistent string theory framework, you again might want to ask, can I actually get a top-down string theory construction of de Sitter vacua where I can study that explicitly? All right. I think I should also say just a few words about beyond de Sitter, because dark energy is not necessarily the same as a strict de Sitter vacuum. We also might try to realize something else, like a time-dependent scenario. And one proposal that has been made, I think last year, is the dark dimension scenario, somehow taking the point of view that if we assume that our universe is described by string theory and we observe dark energy, then dark energy should be realized somehow in string theory. And if we use this observation of a tiny cosmological constant and assume that we are in the asymptotic region of moduli space, then this basically taking Swampland conjectures at face value, this implies a very large extra dimension, which I think is an interesting observation. Of course, a natural question to ask is also, can we realize other forms of dark energy, like a rolling scenario, like quintessence in string theory? In particular, a natural question to ask is whether we can realize that in asymptotic regimes, because then somehow control problems might disappear that we have when we move towards the interior of moduli space. There was quite a lot of attention on this question recently, but potentially trying to realize such a scenario might be as difficult as de Sitter. That's all I want to say. Thank you very much.
Okay, there are some nice questions, but we have time for more. Everybody asked everything during the talk. Yeah.
Yes, on your dark dimension point, I know that there's a paper of Bankin and these people, and then you reacted with a second paper. Will you summarize the debate?
Right. I think the question was about computing the vacuum energy in string theory.
But what is the disagreement and what is the main point between the two cases, between the two groups?
I think, I mean, the main disagreement is whether you really, for example, if you have a extra dimension of a certain radius, whether you find a vacuum energy. It's like constant decay of certain power.
Maybe I can have a couple of comments on.
Can you go?
Well, let's see. All right. Well, got it. So what they do, I think, in the Brankina paper, they propose that, you know, the way you typically compute Casimir energies, right? You know, you could do suppose you're in a circle, so that you don't have issues of curvature in the internal space and stuff, as you pointed out in your paper with Cliff. You basically compute a one loop diagram, right? And then you have one divergence, which, you know, you need to fix typically by assuming that the way you typically fix that is by assuming that when you decompactify the circle, you go back to a Lorentz invariant higher dimensional vacuum, right? And that gives you a unique expression. So they claim that you kind of, the way you compute Casimir energies, you need to regularize in a different way, and you get a slightly different result. So the Brankina paper is really mostly about, not so much about dark dimension, they really talk about dark dimension, but it's mostly about, they propose that there should be a different way to compute Casimir energies of just circle compactifications. The radial dependencies of the Casimir energy they get are different from what you get, not just in dark dimension, but also, you know, in the standard, you know, in the compactification of the standard model paper. Any paper that does Casimir energies, they also disagree with one loop vacuum energy that you get in perturbative string theory, right? For instance, they say that the vacuum energy doesn't go like 1/r to the d in the dimensions. So it's, I think it's a quite drastic proposal. You know, that dimension is one scenario. This is Casimir energies, but there's many other things. I think they can disagree with every other. So yeah, but in a different way, I guess.
Specifically, I have in mind that you know the standard model loops contribute to the vacuum.
Yeah. Ours has a big fine tuning. This is what you're saying, right? So, for instance, in that dimension scenario, you would imagine, okay, there's let's say one interval, and then there's the standard model brane, and for reasons that we don't explain, the tension of the standard model brane has to be tiny, but this is a fine tuning you need. That's the electron hierarchy problem, which we're not claiming to be solving at all. And it needs a big question: how on earth is it possible that you have a brane where the characteristic excitations are like the Higgs scale or something like that, and then the tension is tiny? So we don't explain it at all. The only thing that we're pointing out is that in any scenario like that, with your Bergsus, it's very natural to have something like Casimir energy, and we phrase it a bit more general because if you think about it in terms of the distance conjecture and all of that, but we're just phrasing that in any scenario like that where the Casimir energy is a big contribution to the vacuum energy, unless you do additional fine tuning, okay, for which there's no good reason, you know, there might be there might just be a reason, I don't know what it is, but without any better reason, you get MKK over lambda to the 1/4. You need to do a lot of fine tuning because you need to get lambda to the 10 to the minus 120, and you need to do that with the standard model and everything. So that's, of course, that's the usual problem which we don't solve. You need all this fine tuning to get a small CC. And I say, if you don't do any more fine tuning than that, well then MKK is a further lambda to the 1 quarter. That's what we say. So
how big of a system?
for the standard model, it 10 to 1 part in 10 to get the small CC, right, is 10 to the 120, right? I'm just saying the usual tuning of loops, from the cutoff to the observer electric scale. And then what we are saying is that don't do any more fine tuning than that. And actually, I would say, for instance, the fact that Weinberg's argument works, right? Weinberg's argument is not just that the CC is 10 to the 120 or below. It's also the observation is kind of saturated. It suggests that some sort of naturalness arguments maybe work on the cosmological sector. So we're just taking that a bit like at face value. Yeah. Right, yeah.
That there is one hierarchy problem, right? We don't know
Books.
if we don't solve that, but if you have that, the natural thing that is correlated with a light hour of states. Of course, you can have even more fine tuning to decouple them, but the least fine tuning that we already need for our universe, like the most natural scenario that still remains, is to have also the light hour of states. It's no more than that. So it's not more radical or anything like that.
Okay, thank you. Any more questions? Comments? Can you?
Oh, no, it's about the flux anti-flux idea that you put fluxes positive and negative. For a long time, I actually believed that when you put fluxes which are both positive and negative, when you get something neutral, you get a solution where GTT and G11, GT2, GT3 are not going to be the same. Because generically, when you get a black hole, for example, or a black brains never have the full Lorentz invariance on the word volume. So somehow when you put flux and anti-flux, the naive idea is that you can get a solution, but the solution will not have Lorentz invariance, and therefore when you uplift, you uplift, but you may not get the zeta and so on. So that's something which I don't think people have looked into. Now we did try a construction with Pierre Heinemann where we built an explicit solution which has positive flux on one cycle, negative flux on another cycle, and there for some reason which I still don't understand, GTT, G11, G22, GT3 are still the same. But it's not at all clear, if you ask me why this is happening, I have no idea. It's just something which came out experimentally from the solution we built. But again, the idea is, when you build the zeta and so on, you put negative flux somewhere, positive flux somewhere, you get more mass and charge, then you should be like the black hole, which has more mass and charge, which has GTT different from G11 to 2 and 3, 3. So you should break the Lorentz. And then, okay, once you uplift, maybe you get still the zeta, but one should not start from something with Minkowski invariance and then put an uplift. One should rather start with something which has broken Lorentz invariance, because that's the natural thing which appears when you break when you put more mass and charge on the internal manifold. That's my observation. So I think generically, again, people construct those things, but I think they may cause some problem in getting vacua.
Of course, the moment I discuss non-supersymmetric fluxes, in principle, should also make sure that there's no backreaction effects that are dangerous. For example, by being at a sufficiently large volume or having sufficiently diluted fluxes. Because in the supersymmetric case, the GKP solution basically does the job for me. And also in the moment I have a self-dual flux, that in principle solves my 10-dimensional equations of motion with this solution with the Wolf factor. But if I have a non-supersymmetric case, I might have to work a little bit harder to understand what that is. I'm not sure if this is related.
My expectation was that again, if you break supersymmetry, you get GTT and G parallel to be different. You can break Lorentz invariance in the compactification manifold. This is my expectation based on just the naive black hole solution. But somehow again, in the one example where the full back reaction taken into account, it doesn't seem to happen, and I have no idea why. So I don't know if there's any.
Okay. Any more comments, questions? Have time for one more, maybe? If not, then Søren really answered all the Sitter questions. So thank you very much. Bruno? Okay, we'll go for the second talk in the afternoon. So thank you very much, Bruno, for being here. The floor is yours.
Thanks. And let me also thank all the organizers for this very nice workshop and for the opportunity to speak here. And yes, today I'm going to talk about ADS from higher dimensions. And this is going to be based on some published work and some collaborators, among which Alessandro, which is here, and some work in progress. So let's start. I'm going to be brief on the motivations. We had many, with few wonderful reviews already. And the problem is that we are working in higher dimensions. We come from the top down, and we have to deal with the extra dimensions. And in particular, we want to understand how to describe four-dimensional physics if we start with more than 4 dimensions. And we also want to describe realistic four-dimensional physics, which means many things. And in particular, here we mean to see if we can get de Sitter from higher dimensions. So four-dimensional de Sitter. We have heard about many approaches and constraints and so on. And what I will try to do in this talk is to get these constraints and directly from the equations of motion of generic high dimensional theories of gravity, and discuss how we can evade those constraints and propose some possible solution to some of these challenges. So let's start. We are working with the higher dimensional theory of gravity. So we assume that we have some theory that at low energies reduces just to Einstein-Hilbert in given a large D number, large mean 10 or 11, for example, number of dimensions with some matter content specified by the theory. And we look for four-dimensional physics. So the first thing we do is to, for example, look for vacua, meaning that space-time where we have a four-dimensional vacuum, some internal space, and possibly some work factor. And if we look for these solutions, then the natural thing to do is to just write down the generic equation of motion for this theory and plug the answers. If we do that, we get some set of equations. We get an equations along the space-time and some internal equation, some sort of Einstein equations in the internal space. And these equations specify, if you solve them, you find a vacuum. But to have really four-dimensional physics, we also want to know something about the fluctuations around the vacuum. What's the particle spectrum around the vacuum? And this means, for example, looking at the Kaluza-Klein modes as fluctuation around the compactification around the vacuum. So in general, it's hard to find the Kaluza-Klein modes for general spins, but at least for the spin 2 fields, there is a universal formula that gives the masses of the Kaluza-Klein modes. And is given by this simple operator that only depends on the warping other than the geometry. And so if you're interested in dealing four-dimensional physics, it means that we want to solve these equations, actually the 3 of them simultaneously. We want to know what kind of vacuum we have and what kind of a spectrum fluctuation we have around the vacuum. So we need to solve equations for the vacuum and also be able to say something about the masses or the eigenvalues of this operator. Now, also we want to find constraints that apply to all solutions without going case by case. And well, we already heard about this in the previous talk. There is a very nice constraint you can obtain directly from the vacuum equation, this one. If you assume that the internal space is smooth and without boundary, you can integrate this equation and you get a constraint on the sign of the cosmological constant. And in particular, what Maldacena and Nunez showed that, so you see you have here an integral of certain trace of the stress energy tensor, and this determines the sign of the cosmological constant. And what Maldacena and Nunez showed is that if you only consider fluxes or localized objects such as D-branes, well, then this integral has a definite sign and you're forced to have a negative cosmological constant. But we can consider more general sources where this is not true, and you're going to see an example. And also this is violated for Sopron-oriented planes, as has been already discussed. Now, we would like to do something for the other 2 equations, something similar. For example, can we obtain general constraints? And well, the situation is harder because the equation that we get in the internal space is not a single equation, it's a tensor. This equation is a tensor. And also we have these derivatives of the warping, which we don't know much about. And however, interestingly, this particular combination of curvature and derivatives of the warping has been already studied by mathematicians in the context of optimal transport theory. And what I think is interesting is that what the mathematicians showed is that if you're able to say something about this particular tensor, you are able to control the spectrum of this operator. Meaning that if you know something about this Ricci curvature corrected with this warping, that has a name, it's called sometimes effective or synthetic Ricci curvature with a certain effective dimension, then if you control this tensor, you control the spectrum of this operator. And I don't have much time to get into the details, but I just want to give you some example of what kind of results you can obtain. So the equation of motion has this form, this effective Ricci tensor equal to the cosmological constant plus a certain combination of stress energy tensors. And for example, you can first ask whether you can bound these and have some general properties of these stress energy tensors. And what we found with Alessandro is that indeed you can. And for example, if you only consider again just fluxes or classical sources with positive tension, such as the branes, then this combination of stress energy tensor is non-negative. And this means that you can bound this effective Ricci tensor just in terms of the cosmological constant. We gave a name to this condition, we call it reduced energy condition. It's slightly different than the Malassina-Nunez because here, or particularly slightly different than the strong energy condition because, for example, this applies also to the Romance mass. And so this is a case in which you, if you're in this situation, you can bound this effective Ricci tensor just in terms of the cosmological constant. And here, then we can ask, okay, can we use this to find theorems on the ratio of the spectrum of the Kaluza, on the ratio among the Kaluza-Klein modes and the cosmological constant? And the answer is yes. I'm going to flash you quickly some results here. You can just go to the mathematician and say, now I have a bound on this Ricci, effective Ricci tensor. What can you tell me about the spectrum of this warp Laplacian? And what we find, for example, is that there are lower bounds on the Kaluza-Klein spectrum in terms of some geometric quantities, such as the diameters or geometric quantity known as Chigger constant. And you can use that, for example, to prove that certain solutions have scale separation if you're able to estimate these other geometric quantities. And here you don't have to make any assumption on whether the Kaluza-Klein scale is related to the volume or the curvature, as Thomas introduced yesterday, because here we are already bounding directly the operator that gives the masses of the Kaluza-Klein modes. And or you can try to go the other way around. You can ask, can I disprove separation of scales in certain settings, meaning that you would like to find a lower bound on these the masses of the Kaluza-Klein in terms of the, sorry, an upper bound in terms of the cosmological constant, and you can do, but so far the theorems that we found are not enough to exclude separation of scale, even when you just assume these reduced energy conditions. So we don't know so far whether, because in general you can exclude the separation of scales. But it's true that when you have these reduced energy conditions, so just say classical or positive energy contribution, you get some constraint. So you can ask, what happens if I try to evade these energy conditions? And I want to argue that you have much more flexibility to find interesting quantifications, because when you evade this assumption of positive energy, then you can stabilize flat or negatively curved internal manifolds. And those have a much richer structure that allows to find, I would say, interesting physics. And a way to organize this discussion is in terms of the potential, the effective potential for a generic quantification. For example, when you have, in particular, when you have warping, this was worked out by Douglas, and when he showed that if you take this potential where you have a curvature term corrected by the warping, then finding minimum of this potential is completely equivalent to solving the higher dimensional equations of motion, but gives a nice intuition on what kind of situations you can have. For example, this is a potential for all the degrees of freedom, say all the internal metric degrees of freedom. But if you study it in terms of the volume, for example, first thing you can ask is how can I stabilize the volume? Well, you can look at the potential, you see that the curvature, a positive curvature corresponds to a negative potential, and the positive energy, in the sense of the energy condition we discussed before, means a positive term in the potential here. And then you see that, well, you see immediately how you obtain Malassina-Nunez, because if you have only positive sources here, the only way to find a minimum is with positive curvature, and the minimum is going to be ADS. And this is a pictorial representation of Malassina-Nunez. But then if you allow for energy sources with a different sign, you can have more general situations. For example, you can have a case where you don't have any internal curvature and try to balance the two different signs of energy sources. And this will mean a flat internal space where you, for example, can have an ADS minimum of this kind, and we're going to see an example soon. Or if you start with this situation, then you can try to add negative curvature, which will contribute positively to the potential, and then you hope to find a situation like this, where you have a minimum which is with a positive cosmological constant. And the motivation to that is that if you can stabilize flat or negative curvature, then you have much more freedom and you can exploit more, I would say, more interesting geometric properties. And we're going to see the details of this in a moment. And needless to say that there are many ways in which you can try to discuss to find jitter or other sort of ADS. We've seen many examples. But let me now just focus on one possibility to get this negative energy term, which is in the form of Casimir energies. So when you have a compact internal space, you can ask whether the boundary conditions that you impose on your fields, whether they generate some sort of zero-point energy in the internal space. And they do, for example, if you are able to break supersymmetry, you generically will expect some zero-point energy. And if you have some cycles, for example, in internal space, you can do that by imposing, for example, antiperiodic boundary conditions for fermions. Those break supersymmetry and generate a zero-point energy that you can use as a negative energy sources in the equations of motion. So the idea here is that you assume you have a certain geometry, a certain topology, you compute what are these kind of quantum effects you can generate, and then try to solve the equation of motion semi-classically, making sure that this is consistent, so that the solution, the geometry you use to compute the quantum effect is really a solution of the equation of motion in that geometry when you added that term to the stress energy tensor. And let's see, for example, a very simple example. You can consider M theory compactified on a 7 torus and imposing antiperiodic boundary conditions for fermions there on the torus, and also adding some flux, homogeneous flux in the internal space. And what you get is a potential of this form. So we'll have the negative energy Casimir term here, and the curvature, and the flux term of the potential. So you expect an anti-de Sitter minimum. And indeed, you can do the computation explicitly for a torus. This is simple. You can write, you can solve all the equations of motion theory in this case, or particular 11-dimensional supergravity, and you find an ADS minimum, which is also interesting because it's scale separated. You can compute the ratio of the Kaluza-Klein modes to the cosmological constant in this simple example. You find that indeed you have an arbitrary separation of the internal and the ADS scale, and without needing for the torus to be sub-Planckian. So you can also control all of the other corrections. This is a scale separated ADS vacuum that you get with the Casimir energies. And it has some properties such as it's unstable. For example, we check that it has, it allows for nucleation of a bubble OM2. There is a question. Yeah. Well, the torus is homogeneous. Here, I'm assuming that there are the torus is just a flat torus without any dependence on the point here. So the only quantity here is the overall size. Yes, it is spread over. And the torus is homogeneous and isotropic. There cannot be any dependence here. I'm not allowing for generic moduli of the torus here. And this is just, I'm looking at this configuration. If you are moving away from that, yes, you will generate anisotropies in the Casimir energy. Well, it's related in the sense that here you can, thanks to the combination of these two effects, you can stabilize an ADS minimum without needing curvature. In this sense, it's related. And then with the flat manifold, you have a bit more. You have a decoupling between the curvature scale, which is 0, and the length scales. And that's what's doing the trick here.
Mm-hmm.
Well, small, I mean, great. So as I said, everything has to be self-consistent. So you assume that you have a circle of a certain size, and the contribution will go like the size to the minus d, the contribution to the Casimir energy. That's you can compute. And then indeed you need to make sure that it's self-consistent. So you want to plug in the equation of motion and check what is the circle size that you get to solving the M-theory equations of motion. So you might say, okay, regardless of the size of the circle, you can, in general, you have this formula. But you want it to be strong enough that it has to compete with the classical effect. And this is a question of what the equation of motion are telling you. So you plug in the equation of motion and check when you stabilize, what's the size of the torus. So you would like to be able to do that without needing a tiny torus such that you lose control. Yeah. No, that's a good question. We don't know what these things decays to. The time scale here, I would say. I mean, it's a non-perturbative instability, and I will say yes, probably is the Planck time. The point is that people don't usually care much about if it's if it's already non-perturbative unstable. There is this argument that for an observer at the boundary is going to be killed immediately. So we didn't pay much attention to that, but it's a good question. Okay, so if you have ADS in this way, then you can ask, okay, can I add curvature, negative curvature, and by keeping the same set of ingredients, hopefully finding a potential with 3 terms and a de Sitter minimum. And so to see if that's possible, let's briefly discuss the properties of negative curvature. And so the prototypical example is are hyperbolic manifolds. So hyperbolic manifolds are manifolds that you obtain starting from, for example, hyperbolic space in your favorite model of hyperbolic space, and prescribing a certain way to get a finite volume manifold in hyperbolic space. There are various ways to that, quotienting with respect to some isometry, or equivalently, like a way that I like to describe it is that you have to choose certain polytopes in the hyperbolic space and prescribe some way to glue the faces of the polytopes, identify them, similarly to how to get a torus from a square in Euclidean space. And there are very explicit ways to do that. In particular, there is this recent nice paper that they show how to do it just with right-angled polytopes. So if you do this first, you get a manifold which is finite volume and hyperbolic. And this manifold, interesting, has hyperbolic manifold generically have certain regions which are called cusps, where a cusp is a region where you have certain transverse torus that is shrinking to 0 size very slowly. And hyperbolic manifold generically have many of these cusps. These are interesting for our purposes because this is where you can hope to generate enough Casimir energy to compete with the other effects if you want to use this in a compactification. But we don't literally want a cusp because a cusp is going to shrink to 0 size, and once it gets below a certain size, we might lose control of what's happening. But luckily, there is a way out to this, which is that we can cap off the cusp, so we can truncate the cusp, ending the geometry in a smooth way. And this has been shown, has been proven in this paper by Anderson, that you can do it in generic dimension, and this is sometimes called Anderson filling, which is a way in which you take any cusp or any cusp that you want of the hyperbolic manifold, and you truncate it by shrinking it smoothly at a certain point, and you have freedom to tune the final size of the remaining torus. And this gives a lot of freedom to tune the length of these cycles and the amount of Casimir you can generate, because you can do this procedure for all the cusps of the torus independently. Sorry, of the hyperbolic manifold independently. And after you do this procedure, you get a manifold which is Einstein. So not hyperbolic anymore in general, but is Einstein with negative curvature, with tunable sizes of these cusps. And another important property of this manifold that make them interesting for compactification is that they are rigid, meaning that once you specify the overall volume, these manifolds don't have any modules. Like they don't have moduli hyperbolic manifolds, or even these Einstein manifolds that you get after doing the filling. And this makes them interesting to try to do compactification because it makes the problem of moduli stabilization much easier. So these are the properties of this manifold. Let's see if we can use them to find the sitter. So let's assume we are in the same setting as before, M theory, now with the internal space being these Einstein spaces. And let's see what the potential. Well, the potential has 3 terms, and we have this curvature this warping corrected curvature term, the Casimir term, and a flux term. And the first thing we have to do is to see how to stabilize the volume. And interesting, they scale in this way, with the Casimir term being the negative one and sitting in the middle, such that the shape of the potential is this one. So there is hope to find indeed a de Sitter minimum in this configuration. And what we do in the paper is to argue that indeed you have a de Sitter minimum if you're able to do a certain tuning. And the tuning being that you need to be able to tune the magnitude of this first term, the warping corrected curvature, and you need this to be positive, so that you start with a positive term here, but very small. If you can tune this, we argue that then you are in a regime in which you can have the competition of the 3 terms with a positive minimum. And so how to do this tuning? Well, what I'm saying is that you need to tune a certain integrated quantity, and you have a lot of freedom to do that in these manifolds, because you can, as I said, when you construct them, you can choose the size of all the cusps independently, and by this you have a lot of freedom in tuning the amount of Casimir energy that you have, and you also have freedom to tune the flux by choosing the flux integer. So by combining these effects together, we argue that you have a potential with this shape with a de Sitter minimum. And we can try to do another step. We can try to see if we can solve all the equations of motion on these manifolds. And in particular, this is in general a hard problem, means solving all the Einstein PDEs in this non-trivial manifold. But we can start looking for simplification. One is that most of the action is happening in the cusps. And in the cusp, the geometry is actually simple in the sense that it depends mostly only on the coordinate along the cusp. So you can reduce the problem to just to an ODE problem. And then you can solve all the equations of motion completely. So here we are looking at, this is an answer for what's going on in the cusp. And we try to solve all the equations of motion of 11-dimensional supergravity, so including the back reaction of the Casimir. And you can do that explicitly, and you find indeed a smooth solution with the properties similar to the Anderson field metric. So there is a cycle that is shrinking smoothly, another n-2, so 5-dimensional torus here getting up to a small size, which is enough for it to compete for the Casimir that you build here to compete with the classical term. And on this solution, you can then, for example, check the analytic estimate that I described briefly in the previous slide, and we find agreement with what you can predict from the analytic analysis. And in particular, these are solutions of the full back-reacted equation of motion that are constructed in a large part of the manifold, because these cusps actually compose most of the volume of the manifold. And so the idea is that for each of these cusps, you have one of these solutions. This is how the geometry is behaving in all of them. And then we can ask, okay, can we find a global solution, meaning that we can ask, how does the geometry look like when we combine all these cusps together, these back-reacted cusps together? And we argue in the paper that there is an obstruction, and and you have enough freedom to do this gluing. And to do it explicitly, let's first do a step back and see what happens in the case where there is no Casimir, just flux, and we are just studying the geometric problem. And for example, I told you that you can start with hyperbolic manifolds, and you can fill the cusps so that they get up to you get some smooth manifold with the cusps of a tunable size. And Anderson proved that, and the way he proved that was similar to what we are describing. He constructed a solution in the cusp, a solution only depending on a single variable, And then he argues, and the solution is something we know, is a Euclidean ADS black hole, where the sixth circle that is shrinking is just Euclidean time. And this is negatively curved and has this property. And so what Anderson proved is that you can glue all this together. So he proves that you have all the solution in the cusp, and then you can glue them together such that you get a metric on the overall manifold, which is now Einstein. And it will be complicated in the sense that it will depend on all the coordinates. But he proved that it exists and is somewhat close to this cusp metric. And here we are, for the full de Sitter solution, we are in a similar situation in the sense that we have the back reactor solution in all the cusps. We argue that they can be glued. We don't have a mathematical proof that this can be glued, but we have some estimates that the situation should be similar to the purely geometric case. But already in the purely geometric case, even though it's proven to exist, it's an open problem to construct it numerically. Even forget about de Sitter and Casimir, just construct the metric that Anderson proved to exist. It's an open problem in hyperbolic geometry. And here we're trying to do something similar, but gluing the back reacted cusp with Casimir and so on. And we're trying various approaches to that. One is to use some of the tools that Jim introduced today. So we are trying to use some machine learning methods to do the following. We have the solutions in the cusps, and the only thing that we have to do is to glue them together. And when we glue them, we expect to have some a small modification of the original solution that adds some gradients in the angular direction. And in the overlap, though, they have to solve the Einstein equation, or in particular the equation for compactification, and the overlap should be consistent. And you can try to do with this method. We use some neural network ansatz to parameterize the metric in the different regions, and then we try to glue together in this way. And while doing that for Casimir, it's a complicated problem, but you can, as a first step, you can try to just solve the geometric problem. And this is something we started doing. We have some very preliminary results in the three-dimensional case, and we would like to scale it up and then add Casimir. This is, let me just finish. And this is one way. And you can also try to do something more analytic. Can we do an Anderson-like proof of the gluing of our cusps? It's a bit more complicated than the purely geometric problem, but I don't see an obstruction to that. And with these, I think I'm done. Let me thank you all for that.
Okay, thank you, Bruno, for a nice talk. I think there was already a question just now.
What's the y-axis on your plot? It's some sort of loss, but I don't see what does it depend on?
The loss here, so these are very simple examples, not the case where we glue all the cusps. Here we're just trying to fill one single cusp by minimizing the Ricci. So here is the purely geometric problem. So we have to solve Ricci equal to minus the cost.
Just the loss is Ricci, basically.
The loss is Ricci, so it is required to implement, so to do the Ricci in a differentiable way, as you described, and then use the loss. The situation compared to the Calabi-Yau is it has some simplification. Well, it is more complex in the sense that you cannot use the complex geometry. So here you are solving directly the Einstein PDEs. Some simplification comes from the fact that we already know an approximate solution. Like as in the Anderson proof, we have a solution which is almost solving the equations of motion almost everywhere, and we predict there is just a small modification of that. Yeah. So what we did here was to first retrain the network on the approximate solution that we know analytically, and then just ask the network just to perturb that slightly to solve the Einstein equation network. So we have a starting point which is almost a solution of the problem. That's a difference from the current case.
I see. So, yeah, but then given the neural network result, if you don't regress all the way to zero, do you have in mind to hopefully prove that that also is near some actual solution?
Yes. So that's the goal. Here, for example, in the purely geometric case, we have a proof that exists and that is close to the original one. So,
yeah, so I can cite a reference for you later, something in the PDE literature that's analogous, where they actually take the neural network result and prove that in some local neighborhood there's an actual solution. So it could be very useful for you, those techniques. Yeah, thanks.
Thanks for the talk. Maybe just a lack of intuition. Like you have these cusps, and then you can decide at what volume or length I will cut and I will glue, right?
Yes.
Does this parameter, this length, become dynamical in the low energy effective action when I put the theory, or is a free parameter without dynamics?
So great. So this parameter, so as I told you, these manifolds are rigid. So the fact that you have these parameters might seem in clash with the fact that you shouldn't have moduli, but this parameter is discrete. So it's something that basically you're not free to tune it. So you're free to tune it, but it's
Non-continuously.
So there is the various manifolds are not connected in the sense that you will have some mass gap to go from one to the other.
Okay, thank you.
That's why they are rigid, even though you have this freedom.
Okay, will you then expect that actually they are dynamical, just very massive?
Yes, I don't see why you cannot have a transition between values.
Okay, good.
Yeah.
Thanks.
I guess you asked one of my questions. So the second question, I don't know if it's naive, but how do I see standard model like physics in this kind of spaces?
That's a great question. We need to look at that. I suspect that you can add some M5 brains or intersections of those and then together.
But then I would have to understand some kind of singularity structure in
I
these
guess so.
manifolds.
Yes, we didn't look at it. Yeah,
But is it known? Like people.
Well, is it known is it known here? Well, I don't know, but in general, they just can use Occident theory brains on singularity of the sections on, yes. But whether and what you can do here is something.
Okay.
But of course, it's important to also have any kind of heuristic.
Yeah, Nicola.
Yeah, this is partially related to the last question. Do you expect that in the point in which you realize the gluings, there should be some object?
I expect this move to be, going to be moved.
So you don't have even jumps in derivatives or no?
I mean, no. I expect to really find this move. So, and they actually, this, for example, this is how Anderson proved that you can do these constructions. That he first glue the cast with a certain say a certain kink in the way they are glued. And but then he proved that a smooth one exists very close to that, to Einstein. And expect something similar to the.
Thanks.
Okay, yeah, we have time for one more.
In the plot, you have various spikes. What's going on?
I don't know. Well, this is not very unusual. So it's typical of some. The loss is going down.
No, I know. I see some wiggle everywhere, but there's giant spikes in some places. Did something extra happen there?
Not that I. This was basically just to show if this method made sense and the loss was going down. But I guess there are various to be happening. So maybe there might be some better architecture that can be used optimized here. But if you've seen, say, the curves for training transformers, then you see something much greater than that, and the end result.
Do I understand correctly that the Casimir plays the same role as the orientifold? Do I understand correctly the Casimir plays the same role as the orientifold would?
Yes, it gives this negative energy.
Yeah. And then, as Thomas asked, also in this hyperbolic case, it's just a constant contribution. It's not point dependent.
Here,
yeah.
No, that's why the situation is a bit harder, because here this is not a torus, it's not a global torus. It has some regions where there is this torus, but its size is shrinking smoothly, but its size is changing. So that's why the geometry is a bit more complicated. It's not now it's not isotropic anymore. You need to consider how locally the Casimir is generated, and this is what's generating a non-trivial work factor. And for example, you can see it explicitly in these solutions. These are solutions where the Casimir is properly taken into account in the sense that it depends on the position along this torus direction. It depends on the size of the torus. And this is why you have a work factor, which is. But from here, you can just solve the set of the
Thank you.
Okay, and I think we're out of time. Anyway, we'll have a discussion on the city later on. So let's thank Bruno again. We now have a coffee break and resume at 4:15.
when it's 20 minutes.
Okay.
And then
Oh, do I have? Okay. Okay, thank you. I will try and. Does it work?
Yeah, now it works. So basically,
Okay.
laser and next and previous.
Okay, great. Okay, thank you. Okay. Oh, yeah. Whoops, I don't know if that's going to stand.
Okay. Welcome to the last session of the day. It seems we can start. So we're happy to start with Susha telling us about her last digital work.
Okay, hello everyone. You can hear me, I think, right? Yes. So indeed, I will be talking about transient de sitter vacua from interacting dark sectors. This is work done in collaboration with Ed Hardy and our student Joaquim Gomez. And I also can't resist mentioning very briefly some work by my very excellent student Marco, who is somewhere in the room, that relates to some of our discussions from yesterday. Oh, sorry, I should. Okay. So, as we all know, runaway moduli are, of course, ubiquitous in string compactifications, but despite lots of recent effort, it seems that they always seem to be too steep to source quintessence. Perhaps this is not so surprising. If we were to be having some accelerated expansion in the asymptotically along these runaway directions, we'd have to deal with time variation of fundamental constants unobserved, fifth forces, and we'd have to face the question, if we have eternally accelerated expansion that leads to cosmological event horizons, we'd have to face the question of how to formulate quantum physics in the presence of these event horizons. All that is to say that it's probably fair to say that metastable de sitter vacua via quantum effects, probably with numerical control, with some anthropics to explain the cosmological constant problem, is probably still our best explanation of dark energy, and I'm afraid that won't really change at the end of the talk. But still, I guess we all agree that it's important to think about possible alternatives. So let me mention just a couple before getting into the main part of the talk, a couple of ideas that I think are interesting. So there's been this work recently by Dimitrios and others who have found that one can actually obtain asymptotic accelerated expansion from steep runaway directions if the space-time, the 4D space-time, has negative spatial curvature, so an open universe, and that's precisely in that case, the event horizon, the position of the event horizon goes off to infinity. So it seems like an interesting observation. The big question, of course, is how relevant that might be for cosmological observations, and that's something that we're thinking about now. Another direction that seems, of course, important to study is the relatively unexplored area of string theory, which is non-supersymmetric strings. Will these offer an alternative place to search for accelerating solutions? So far, it seems that we just find more no-go theorems, and here I just mentioned these results from Marco, considering type 2 compactifications with some maximally symmetric space-time, times another maximally symmetric space times a Schurz-Schwarz orbifold. So breaking supersymmetry with the Schurz-Schwarzing, with fluxes which can be tadpole free, and potentially curvature from this space here. So the SUSY breaking and the gives rise to Casimir energies, as we've heard just now from Bruno, potentially a way to evade the Maldacena-Nunez, but unfortunately we seem to find still no de Sitter solutions. As an aside, this setup does lend itself to finding non-supersymmetric ADS with parametric control. They're scale separated, only partially scale separated. Yosif will tell us that we're cheating, but okay, they've been found, these non-SUSY solutions. Unfortunately, we haven't yet exhausted all the possibilities, but it seems like they all seem to be tachyonic below the BF bound. But I should mention, Alessandro was telling me in the coffee break this morning, and it came up in some of the questions, there's earlier work finding non-SUSY ADS vacua, which are at least perturbatively stable, which I'm sorry, they're not in my reference list, including Alessandro and Gaiotto. Okay, so that was just some general motivation. So this is a real part of the talk. My plans, I'll be talking about string-inspired, shall we say, mechanisms to dynamically stabilize steep runaway directions into a transient de Sitter vacuum. This can be done consistently with cosmological observations and consistently with the swamplands conjectures. And so this is how I'll present to you those results. So I'll present the idea how interacting dark sectors can lead to the transient de Sitter vacuum. I'll show you that despite the Lagrangian potential having no de Sitter vacuum. And then I want to point out the observational constraints. I'll mention some the fine tuning the status of the fine tuning in the scenario, the swampland conjectures, and then I'll give you some outlook. And of course, a very important part of that outlook is an embedding into string theory, which we're only really just beginning to think about. Okay, so this is so I have to apologize that there's not much string theory in this talk. The talk will focus on the dark matter, dark energy scenarios. I won't have time to discuss, but you can look into the paper if you're interested. Other parameter spaces are also possible with dark radiation, kind of helping to get dark energy, and also multi-field quintessence scenarios. And another thing I will not discuss is the cosmological constant problem, I'm afraid. Okay. So here's the idea. So we'll just have a simple toy model, which kind of from which you can see all the physics and get the intuition. So just two interacting hidden sector scalar fields with canonical kinetic terms and potential energy functional. The potential energy functional will take this form. So this is my field psi will play the role of the dark matter. It has a mass term. My field phi will play the role of the dark energy. And I'll just assume that it has kind of a Higgs-like hilltop potential with a de Sitter maximum, or a steep runaway potential, exponential runaway. And for the talk, I'll be focusing on that steep runaway. Key is that there will be this quartic interaction term between the dark matter field psi and the dark energy field phi. Now, without that interaction term, so I'm parameterizing. I have these parameters here, lambda, which is kind of giving the field range of my field phi, so it's somewhere below m Planck, and my quartic coupling are right in this way in terms of a mass scale m int over lambda, the field range of phi. When the quartic coupling goes to 0, is it equal to 0? Either phi or psi could source a slowly rolling quintessence, but of course only by fine-tuning the initial conditions, say to the top of the hilltop, or with phi rolling first up its exponential potential and then down, or with some dangerous large field distances. And what I'll show you now is that when the quartic interaction term is non-vanishing, with psi behaving either as dark matter, dark radiation, or some subdominant dark energy component, this psi can dynamically stabilize phi near to phi is equal to 0, where it can source our observed dark energy in a transient de Sitter vacua. So here's the mechanism for dark matter. So let's just assume, to begin with, some Friedmann-Robinson-Walker background. There's the energy density, which I'll assume is dominated by this contribution to the potential energy from my field phi. This is, we can solve numerically the full cosmology, which we'll do below, but just to get the intuitive picture, we'll make this assumption that the dynamics of psi is dominated by its mass term, just so that the dynamics is linear, things are simple. Of course, psi just obeys its Klein-Gordon equation in a FRW background. If psi starts away from its minimum, so somewhere up its quadratic potential, anywhere really up its quadratic potential, and psi has a mass which is greater than the Hubble constant today, then it will at some point in the history of the universe, it will begin to oscillate in its quadratic potential. This is its solution. So it has these oscillations, which you can think of as a collection of scalar particles oscillating coherently with the frequency set by the mass, and the energy density in these oscillations evolves as matter. Okay, so supposing that the oscillations are the oscillations here are fast enough that we can just average over them, then the quartic interaction term in the Lagrangian in this background of psi sources an effective mass contribution for phi. You can solve then the equation of motion for phi, or as a first instance, just find whether its effective Lagrangian potential has a minimum, and indeed it does. This is the minimum of the potential for effective potential for phi in the background of psi. That's the principal branch of the Lambert function, the special function, and so we see that phi can be held in a de Sitter minimum where it sources dark energy. Okay, so that's kind of the very simple picture. The minimum for phi, again, it takes this form. It depends on the average of the oscillating dark matter field. The solution exists for any value for psi squared. But remember that even if we average over the oscillations, the amplitude of the oscillations is, of course, decaying because of the Hubble friction. That leads to a time dependence in the de Sitter minimum. And if we want to satisfy observational constraints that the dark energy does not evolve too much, this ends up giving a bound on an upper bound on the number of e-folds of accelerated expansion that one can obtain. We can do a bit better than that as well. So we can kind of think about the full dynamics of phi in this oscillating background of psi. Roughly speaking, phi obeys a mature equation with there's a second order ordinary differential equation with an oscillating stiffness coefficient, which is coming from those oscillations in psi. The coefficients of the in the mature equation are time dependent. This might be familiar to some of you who have looked at reheating, preheating. This is parametric resonance. Okay, and there's the solutions to this mature equation are well known, and they take this form. And what we learn from all of this story is that phi in general, so our dark energy field in general undergoes can undergo a parametric resonance instability. So away from its minimum due to this coupled behavior between the phi and the psi, which would end the dark energy domination. We can evade that by ensuring that the Hubble friction is enough to suppress this growing mode, and that puts upper bound on the mass of psi ultimately. So right, so m psi has to be less than around 15, the Hubble constant today. At late times, so the amplitude of the oscillations of psi are getting lower and lower. At some point, you know, its influence will drop out, and will effectively go to the exponential runaway again, and the solution will so the phi will then go to a global attractor, non-accelerating scaling solution down at steep runaway potential, which is well known, in which the energy density remains a fixed small fraction of the total energy. So it's a kind of transient de Sitter, which and the final endpoint is a non-accelerating scaling solution. Okay, so that's kind of the general intuition. One can then just go ahead and check all those ideas by solving numerically the equations of motion. The parametric resonance condition that it must not end, the parametric resonance must not end the dark energy E-block too quickly. Remember that put an upper bound on the mass of psi. That means that psi will kind of begin its oscillations. It will get unfrozen by the Hubble. I mean, you know, it will start off. It's a light field. It will start off being frozen by the Hubble friction. At some point, as H falls, psi begins to oscillate. But that will, because psi is so light, that will happen well after matter radiation equality. And what that means is that psi cannot be all the dark matter. So when we're solving the full cosmology, we'll put in kind of an additional contribution of dark matter, which is the dark matter that we observe. This is just one example of solutions, like some parameters which reproduce our lambda our cosmology, the lambda CDM model. So this is, I don't know how visible that is to everyone, but this is the equation of state parameter with respect to the scale factor, and we match the equation of state parameter of lambda CDM up to some point, actually it's around 0.5 e-folds after today, when then we go to the effectively a matter domination. And how much time do I have? Okay, great. So and so this is what's happening to the field. So psi is slightly lighter than phi. So at early times, we've just kind of imagined that, you know, something like inflation sets up the initial conditions, and both fields are starting somewhere away from their minimum as the universe cools and H falls. First of all, phi will be unfrozen from its minimum, and it will start to oscillate around its effective de Sitter minima. Pretty soon it will start behaving as dark energy as the amplitude of the oscillations fall. And then later psi will also start rolling and behave as a subdominant dark matter component. During that kind of complicated coupled behavior, phi effectively gets locked near to its minimum, and then finally the amplitude of the psi oscillations gets so small that phi begins to roll off down its exponential runaway. So the upshot is that there's we can get viable, cosmologically viable models with no fine-tuning of the initial conditions. There's no super Planckian distances, all the field ranges are sub-Planckian. There's no fine-tuning between the Lagrangian parameters, and it's consistent with the cosmological observations. So there are potential observable signals. We have this component of dark matter, extremely light dark matter, for which there are bounds, and whose bounds will improve with future CMB observations and the square kilometer array measurements. Potentially, we can have variation of the equation of state parameter of dark energy if we're near around the bounds of parameter space. There could be some spatial variation in the equation of state parameter depending on how the initial conditions are set up for our dark matter field. And as I'll speak a bit more about that, there are forces as a result of these extremely light fields. So here's our parameter space, which is allowed, and I think there's not too much I want to say, just if that again, I'm not sure how visible that is. There's our upper bound on the mass of psi to avoid too early parametric resonance, which would take us away from the dark energy epoch. If the mass of psi is too light, you just get to a quintessence limit, which is maybe less interesting. There are some bounds require, that the coupled behavior doesn't lead to too big oscillations in phi, while psi is oscillating, which would lead to too much variation in the dark energy. Okay. So I should make some comments on the fine tuning in the scenario, in particular thinking about what one might hope for from a UV complete model. So we need light scalar fields. In fact, all the scales in the problem are set around H0. And that's similar to quintessence, and comes with the problems that quintessence models have. So there's one good thing is that at least this quartic interaction. So the quartic interaction itself has to be small for the mechanism to work. The quartic interaction, of course, itself would lead to UV sensitive contributions to the masses of psi and phi. So there'll be loop corrections to the masses of psi and phi due to that quartic interaction. And that at least does not require too much fine tuning. So there'll be sufficient, the loop corrections are sufficiently suppressed, provided that the UV cutoff is not too far from the Planck scale or from lambda. There'll also be corrections from gravitational couplings to visible sector states, say with mass m, and there we would require some fine tuning for any states that are for the states that are less than greater than, say, GeV, and there'll also be corrections from heavy string states, and all of this is, of course, these last 2 points are similar to quintessence, and one can, aim to do some model building. Perhaps sequestered Susie can help with these issues. Before closing, let me just, some of us might want to check, is the scenario consistent with the Swamp-Planck conjectures? As I already emphasized, all the field ranges are some Planckian, so there's no worry about control of the effective field theory from that point of view. the de Sitter swampland conjecture can be satisfied for some ranges in windows or parameter space. One can check that analytically, kind of for the whole field range of psi and along the minimum for phi, and one can then just check numerically that the swampland conjecture is satisfied for the full cosmological trajectory. And because we just have a few e-folds of accelerated expansion, the Transplanckian censorship conjecture is also satisfied. So let me end with some outlook. As I've said, a light hidden dark matter scalar with this a mass kind of around Hubble scale, slightly bigger than Hubble scale, can stabilize a steep runaway modulus in a transient de Sitter vacuum via this quartic coupling with our dark energy field, which also has a mass not much bigger than H0. We can get a natural cosmological history without fine-tuning of the initial conditions or super Planckian field distances. So in that sense, it does somewhat better than kind of vanilla quintessence models. And there's only a transient de Sitter epoch, so we don't have to worry about the Tanner acceleration, cosmological horizons, and the EFT seems to be consistent with the swampland conjectures. The UV sensitivity from the quartic coupling, which is key to the scenario, that UV sensitivity is mild, though you need some sequestering from the visible sector to suppress fifth forces. It's not much difference from quintessence. One can wonder if axions would play a role in helping there. And other parameter spaces are possible, with psi playing the role of dark radiation or multi-field quintessence scenario. Maybe one thing that's worth pointing out is that for the dark radiation, the scales are different, and like the masses and the coupling scales are fixed by Rho dark energy, so by around milli-electron volts rather than 10 to the minus 33 electron volts. Embedding into string theory would of course be interesting, and in particular because we have these light scalar fields and we have to avoid the fifth forces, we'll have to think about, you know, that whatever the fields are, they have to be some kind of local moduli rather than volume moduli or the dilaton or whatever to be able to sequester from the visible sector. Okay, and I will leave it there.
We have time for questions. Yes.
Very nice, Susha. Okay. Any hints about your work in progress on string?
Well, I'd be very happy to hear if any of you guys have ideas. We're really just beginning to think about it. So it's true, of course. So I wanted to emphasize kind of the steep runaway thing. But if we were to start with the hilltop, for example, instead, then that's just the same Lagrangian that's the hybrid inflation Lagrangian, and there have been attempts at string embedding of hybrid inflation with D-branes and so on. So that's and that would provide us also with the local aspect, very characteristic of the fields that we need. So I think that's probably the first thing to think about is it needs to be local, and we do. Maybe one thing that's quite tricky is that so it doesn't necessarily need to be a quartic coupling. It just needs to be a coupling, that has the right kind of shape, the bit that's in the right direction. So maybe I'll continue. Otherwise, I'll just babble. I'll continue after.
And any attempt to do this early dark energy using this?
Yeah, that's a really good question, and also that's also really nice because then if you exit after the exit of early dark energy, there could be hope for proper signals. So that is a really nice question. So after kind of we had like this thermal dark energy scenario, which was kind of the dark radiation version of this. There have been some works in kind of that, in using that kind of scenario for early dark energy by Martin Sloth and others, and I think actually they've done quite a lot in that direction, which is interesting.
When this equation of state parameter goes to -1, that's, I guess, when you want to be today, right?
Exactly, yeah.
And that is kind of a why now problem, isn't it? I mean, you need to do something to make that happen.
Is it a why now? I mean, so in some sense, it's nice that it's fairly independent of our initial conditions, that we do end up independently of the initial conditions, as long as you're starting somewhere away from the minima, right, which is like the generic thing that you'd expect, then you get to this de Sitter vacuum. And then I guess it's just a question of, I mean, we're not explaining why the rho dark energy is the same order of magnitude as the matter. That's true.
Okay.
And that's, I guess, in particular because the scales didn't work, right? Because we needed our mass of the dark matter to be super light, so it couldn't be all the dark matter. And so, I think we don't. That's true.
Yeah, about the latter point. So, wouldn't you say that you somehow solve, on the one hand, the cosmic coincidence problem, and on the other hand, I would still say naively the cosmic constant problem, because in this scenario, the dark energy will always be of the same order as matter density, right? So, am I wrong?
I'd be very happy if you're right. I think I have to think about that. No, to me, it did not seem that we're solving the dark, the coincidence problem, because, because I've put in the scales by hand. So
yeah, but you could say you put in the scales by hand, but the scales have to be consistent with what we observe. So dark matter the density should not be higher than the matter density we observe. So I don't know.
Maybe you're right. I need to think about it. Yeah. Thanks for the question. Yeah.
Thank you. I think it's time to move on. So thank you again. Have a nice talk. Go on with the de Sitter discussion session.